Before we talk about our next segment on eclipses, I wanted to highlight something that some of you all talked about in the discussion from last week about auspicious alignment. And some of you read the article about Manhattanhenge. Manhattanhenge is a similar idea to Stonehenge. At Stonehenge in England, on 2 days a year on the summer and winter solstices, the stones of Stonehenge are aligned such that you can see the sunrise and the sunset on the solstices directly in between these well-aligned stones. The streets along 34th Avenue in Manhattan, and you've got the tall skyscrapers on either side of that street. And on 2 days a year, the street is aligned such that on 2 days a year, you can see the sunset directly between the skyscrapers of Manhattan. This does bring up an important thing that I'd like to talk about that I totally neglected to talk about, and that there's only 2 days a year when the sun truly rises in the east and sets directly in the west. And those 2 days are the autumnal equinox and the vernal equinox, the beginning of fall and the beginning of spring. So let me show you what that looks like, at least for the beginning of fall, which is coming up in Stellarium. So here we are on the first day of autumn, September 22nd for us this year. In the morning time, we're facing directly east. I removed the effects of the atmosphere here so that we can see the sun against the background stars. And so we see that on the beginning of fall, the sun really is truly rising directly east. Now, let's see what happens. South is over here, okay? So let's see what happens as we step forward a few days or a few weeks in the future and look at where the sun rises. Now we just move forward a whole month from our autumnal equinox, the beginning of fall, and we see that the sun is now rising not directly due east, but closer to south. And then if I go forward even another month, and I'm gonna adjust our time here, I've moved forward even more another month, and sunrise is even closer to the south, moving away from east. So it's moving southward as it rises as we get toward the winter solstice, the beginning of winter there. And so on the winter solstice, we'll see the sun rising furthest to the south away from east. And then as we move forward in time, going closer to the beginning of spring, so we're going to progress through the winter and get closer to spring, after our winter solstice, we're going to start to see the sun move back toward the east again whenever it rises. So let's go back let's go 2 more months here. Okay, so here we are in February, and we see that the sun has moved back further to the east. And now I've progressed forward to the beginning of spring, the vernal equinox. And then we see that on that day, yes, the sun is rising again directly in the east. So the moral of the story is that only on 2 days a year is the sun going to rise directly in the east and set directly in the west. Those 2 days are the beginning of fall and the beginning of spring, the fall equinox and the vernal equinox. And then as we move away from the autumnal equinox towards the winter solstice, the beginning of winter, the sun is going to rise further and further and further to the south. And once we hit the winter solstice, then the sun is going to start rising closer and closer and closer to the east again until it rises directly due east on the first day of spring. And if we do the same thing, we go over and look at that same process happening in the west for sunset. The sunrise is directly to the east. If we watch the same process happen over here for sunset, we would see a similar thing. For me, as a solar scientist, the topic that we're going to be talking about now, about solar and lunar eclipses, is really special to me. I've seen at least 2 solar eclipses, total solar eclipses, and as a solar scientist, they're super special, and I'll share with you why in this video here. Eclipses occur when the sun, earth, and moon are directly in line with each other. So here we have the sun and the moon and the earth all along the same line to create a solar eclipse. A solar eclipse occurs when the moon passes directly between the sun and the earth, and the moon casts its shadow on the earth, causing, during the middle of the day, the sky appear to become dark as if it were night for just a few minutes. And also the temperature does drop a little bit too, because there's less of the sun's energy, sun's rays striking on our planet for those few brief moments in time. Now, during a solar eclipse, we've got the moon, again, passing between the sun and the earth. The moon perfectly blocks out all of that light coming from the sun's surface, and it allows us to see what we call the solar corona, the sun's outermost atmosphere. The corona is like Latin for crown. So you see this crown of the sun's outermost atmosphere. And this is caused by magnetic fields that are attached to the sun's surface and that extend out into space. And we will also talk more about the sun and its magnetism later on, which is, again, my favorite topic because that's the research that I do. So here's a solar eclipse as seen from space. This is the shadow of the moon. So there are 3 types of solar eclipses. And these types of eclipses are called total, partial, and annular. And you must have a new moon in order to have an eclipse. Why? Because the moon has to be directly between the sun and the earth. And that only happens whenever you're in the new moon phase. So here's the sun, here's the earth, here's the moon. And we have to have the sun coming through, striking the backside. The light from the sun is striking the backside of the moon. And so the part of the moon that we see from the Earth's surface would be new moon. It's not going to be illuminated from the front by the sun, but instead illuminated from the back. During an eclipse, the part of the eclipse that we call totality is the time when the sun is completely blocked by the surface of the moon. Here are the 3 types of solar eclipses. We have the partial, the total, and the annular. So the partial happens when the moon doesn't entirely pass directly in front of the sun. It passes maybe off on the corner of the sun. And so we just get a part, so the moon would be sitting right here. The moon just covers a part of the sun, but not all of it. During an annular eclipse, again, that happens when the moon is a little bit further away from us than usual in its elliptical orbit around the Earth. And that means that the moon appears to be a little bit smaller in the sky than the sun does. And so what we see then is the moon here and this little ring of the sun around it. And this in the middle is what we really want to see. This is a total solar eclipse where the moon perfectly blocks out all the light from the sun's surface and it lets us see the solar corona, the sun's outermost faint wispy atmosphere that we can't see on a normal day because the light coming from the sun's central disk is just way too bright and it keeps us from seeing the sun's halo. So total solar eclipses on Earth are a cosmic coincidence. I like to use that word. The only reason we can have these perfect solar eclipses on our planet is for one very special, auspicious reason. And that reason is the moon's diameter is 400 times smaller than the sun's diameter. But the sun is 400 times farther away from the Earth than the moon is from the Earth. And all of those perfect coincidences mean that the size of the moon in the sky as viewed from Earth and the size of the sun in the sky as viewed from Earth are about the same size. And so whenever you have a perfect total solar eclipse, you've got these perfect ratios that are operating together with each other. Such a thing is really going to be hard to come by on any other planet, on any other solar system. The odds are really unlikely that you would have these perfect ratios so that you could have these perfect eclipses. And it's really crazy that we have this here on our planet. Here's an example of what a solar eclipse looks like from Mars. So on Mars, there's a rover. There's a couple of rovers, but there's a rover called Curiosity. And here's what Curiosity looks like on Mars. And Curiosity took this photo of one of Mars's moons passing in front of the sun. So this was a solar eclipse on Mars. This moon, Mars has two fairly large moons, and this moon here is called Phobos. And so you can see that Phobos isn't this beautiful circular moon like we have. It's sort of a little bit like a potato. And Phobos here is crossing or transiting in front of the sun. And so we see here that the relative size of Phobos compared to the sun, as seen from the surface of Mars, is not such that that moon could perfectly block out all the central part of the sun to let us see the solar corona from the surface of Mars. And here's another example of a solar eclipse. This is a picture of a solar eclipse taken in 2017 from the surface of the Earth. This is what was captured. So again, we have the sun way in the background. Here's the moon in the new moon phase. So all the light from the sun is striking the back side of the moon and not the front side. And because of this perfect ratio again, we get that the moon is perfectly blocking out the sun's center, and it lets us see this beautiful solar corona. These arches, these loops that you see here, those are loops of magnetic fields, giant loops of magnetism extended off of the sun's surface. And so what happens is that hot particles from the sun's upper atmosphere become attracted to these lines of magnetic field, and they get stuck there and they sort of glow. And that's what we can see in these beautiful images here. Here's a map of total solar eclipses that have happened and are coming up. Total solar eclipses are fairly rare. You have to usually wait every year or every year and a half in order to find one somewhere on the surface of the Earth. So let's see. Here was the one in 2019 that I saw that went through Chile. The next one, oh, here is the one in 2017 that went through most of the United States. Maybe some of you got to see it. I got to see it up in Portland, Oregon, or near Portland, Oregon, and Salem, Oregon. And then the next one that we'll be able to see in the United States is in 2024, April 8th, 2024. And it's going to pass kind of through Texas here, and it's going to pass up through Indiana, and it's going to exit up here through Canada. So we won't be able to see a total solar eclipse here in Cleveland. You're going to have to drive a few hours north in order to catch one. So now let's talk about lunar eclipses. A lunar eclipse occurs when the Earth passes between the sun and the moon. So instead of the moon passing between the sun and the Earth for a solar eclipse, for a lunar eclipse, we have the Earth passing between the sun and the moon. So for a lunar eclipse, here we have the sun, here's the moon, and here's the Earth between. And so the sun is illuminating one side of our Earth, and it casts a shadow onto the moon. This shadow gives the moon sort of a reddish color. Why is it a reddish color? Well, that happens because the light from the sun is passing through our Earth's atmosphere. Some of that light gets bent away. Some of the colors more toward blue get bent away, but some of the colors more toward red get bent sort of around the Earth and end up focusing on the moon's surface. And that's why it appears to have sort of a red hue. So just like there are 3 types of solar eclipses, there are 3 types of lunar eclipses. These 3 types of lunar eclipses are called total, partial, and penumbral. So you get a total lunar eclipse when the moon passes entirely through what we call the umbra of the Earth. So the umbra is a part of the shadow from the Earth where all of the sunlight is blocked. So right here in this darker cone here, all of the sunlight, all the light from the sun is entirely blocked by the Earth. And so you don't have any light from the sun coming within this part here of the shadow of the Earth. Okay, so if the moon is right here in this part of the shadow, in the umbra, where no sunlight is escaping into, then you have a total lunar eclipse. Okay, you have a partial lunar eclipse when part of the moon passes through the umbra. And then you have a penumbral solar eclipse when the moon passes through this part of the shadow called the penumbra. And the penumbra is the part of the shadow where only a portion of the sunlight is blocked. So here in this darker gray triangle, all the sunlight from the sun is blocked in this part of the Earth's shadow. And this part of the Earth's shadow in the penumbra, not 100% of that sunlight is blocked. Some of it filters through or leaks through, and that's the penumbra. And so here on the far right, you can see what these different types of eclipses look like, lunar eclipses. In a total lunar eclipse, the surface of the moon looks a little bit reddish. In a partial lunar eclipse, part of the moon is lit up and another part is darker. And then in a penumbral lunar eclipse, it's really hard to see, but the moon is just a little bit less bright than it should be. The moon must be in the full phase in order for you to have a lunar eclipse. Why? Because for the lunar eclipse, we have to have the sun and the Earth and the moon in alignment like this, okay? And if the Earth were just a little bit out of the way, then we would have the sun illuminating the whole side of the moon that's facing toward Earth. And then only when the Earth passes directly between this line from the sun and the moon do we get that shadow from the Earth being cast onto the surface of the moon. Now, we don't have a lunar eclipse every full moon. The reason why is because our moon doesn't exactly orbit our Earth in a flat plane. The orbit of the moon around the Earth is tilted a little bit. So if this blue line here is the orbit of our Earth around the sun, and this white path here is the orbit of our moon around the Earth, we see that the orbit of the moon around the Earth is inclined a little bit to the orbit of the Earth around the sun. And that little bit of inclination means that we're not going to have a lunar eclipse every full moon.